Okay, so in electrochemical cells, we connect two different electrodes together. One of them, for example, is zinc placed in a solution of zinc ions, and the other is copper placed in a solution of copper ions. And we said to get standard conditions that both solutions should have a concentration of 1 mole per decimeter cube. The temperature should be 25 degrees Celsius or else 298 Kelvin. And we connect the two solutions using the salt bridge, which contains a saturated solution of potassium nitrate, to connect these two solutions together so that ions can move in these two ions. And we connect these two electrodes using a wire. So what happens? We said that in case of the zinc electrode, the zinc would prefer, as zinc, of course, we measured the E0 value, the standard electrode potential of zinc, and it was found to be minus 0.76 volts, which means that zinc would prefer to dissolve in its solution, forming more zinc ions, and the zinc would dissolve in its solution, forming more zinc ions, and electrons are formed on the metal electrode. And so electrons will pass, if there was no voltmeter placed here, then electrons would pass from the zinc electrode towards the copper electrode, where we said that in the copper electrode, the copper ions would gain electrons to form copper metal. We said that the E0 value for this copper ion copper electrode would be plus 0.34 volts, which means that copper ions would prefer, since we have a positive value, then the forward reaction is the favorable reaction. And this means that copper ions would like to gain electrons. And so electrons would move from the zinc electrode towards the copper electrode. We say that the electrode from which electrons are generated, we call this the negative electrode. We call the zinc ion electrode, we call it the negative electrode, and also we call it the anode. But for the copper electrode, where it gains electrons, we are going to call it the positive electrode or the cathode. Okay, so what if we connect these two half cells together? What will be what we call the electromotive force, or the E0 of the cell? We are going to measure here what we call E0 cell, which is the electromotive force that is measured between these two electrodes or two half cells. So if we connect them together without any voltmeter, then we will see that electrons would move from the negative electrode or the anode towards the positive electrode or the cathode. But if we place here a voltmeter, which has a high resistance to prevent the flow of these electrons, then the voltage that is measured here is going to be called the E0 cell, which we sometimes call it the electromotive force. But of course, here in this syllabus, we are going to call it standard electrode, the standard cell electrode. The standard cell electrode. It's the voltage that is measured between the zinc electrode and the copper electrode. Okay. Now, what happens here is that we have two reactions taking place. In the first half cell, the zinc ions plus 2 electrons give zinc. E0 is minus 0.76 volt. And in the second half cell, the copper ions plus 2 electrons give copper, where the E0 is plus 0.34 volts. And so the overall cell reaction would be zinc metal plus, because of course the zinc, as we said, would lose electrons to form zinc ions, and the copper ions would gain these electrons to form the copper metal. So the overall cell reaction is that we add these two half cells together, the electrons goes, or they cancel together, and we get the overall cell reaction as that the zinc metal reacts with the copper ions to form zinc ions plus copper metal. Now, Now here, instead of always drawing in this way, instead of always drawing our cells, we can write what we call cell diagrams. What are cell diagrams? Cell diagrams are, as we call it, shorthand notation. We call it a shorthand notation. It means that we are going to write in shorthand notation. It means that we are going to use a certain cell diagrams in order to represent our cells without drawing. We can write in a shorthand notation so that we do not draw these cells. But if we write these shorthand notations, or what we call the cell diagrams, we can determine which one of them is on the right-hand side, which one of them is on the left-hand side, and what is the E0 cell of them. So, for example, in this cell diagram, okay, in these cell diagrams, we are going to write always, if we are going to represent half cells only, we start with the positive ions, and then we put a vertical line and then the metal. This shows that there is a phase boundary between the ions and their metal. For example, if I place a metal in a solution of its own ions, we write this half cell, we write the positive ions first, aqueous, and then we put a vertical line and then the zinc metal. And we write beside it the E0 equal minus 0.76 volts, which means that this is the standard electrode potential of the half cell at which a metal is placed in a solution of its own ions. This vertical line represents the phase boundary between the metal and the solution. Or else I write, for example, magnesium ions, and then this vertical line, and then magnesium. Also, it shows that there is a phase boundary between the copper metal and the copper ions. Okay, and E0 value equal plus 0.34 volts. So half cells are written in this way, what we call cell diagrams. And beside each half cell, we write its standard electrode potential. Now, what if we have a solution? As we measured, we had two aqueous solutions like iron plus 3 and iron plus 2, and we wanted to measure the standard electrode potential between iron plus 3 and iron plus 2 ions. We constructed a cell, as we have seen, at which we place a platinum metal in a mixture of these two solutions. So in order to express it in the cell diagram way, we write the platinum first, platinum solid, and then we put the vertical line, which represents the phase boundary between the platinum wire and the mixture of solutions. And then we write iron plus 3, comma, iron plus 2. It means that both iron plus 3 and iron plus 2 are present as a mixture in the solution, and platinum was a metal that is placed in them in order to be connected to the voltmeter to the hydrogen electrode. And so the E0 value is plus 0.77 volts. If we want to express the standard hydrogen electrode alone, so also we start with the ions, and then we put a vertical line, and then we write hydrogen gas, and then another vertical line, and we put platinum solid. Okay? Do you hear me well? Can you hear me properly, or shall I change my notes? Hello?
Yes, miss, I said change it.
Can you hear me, or shall I change my net?
Miss,
Yes. I will change my net, okay? Hello?
Yes, Miss.
Okay. We're going to continue. Okay. So we said that if we are writing the cell diagram or the shorthand notation for the hydrogen electrode itself, we write hydrogen ions and then a vertical line, then half hydrogen gas, then another vertical line, and we write platinum. Okay. Now, what happens if we connect two half cells together? Like as we said here, we are connecting the zinc electrode together with the copper electrode. So usually we are going to start to write from the left-hand side with the electrode at which electrons are released. As we said here, zinc, as it has a negative, the zinc has a negative standard hydrogen electrode. It means that the zinc metal would prefer to dissolve in the form of zinc ions, and electrons come out of it. It's the anode, or we call it the negative electrode. So usually we write the negative electrode on the left-hand side and the positive electrode on the right-hand side. So here in the cell diagrams, we are going to do the same. We are going to write the zinc electrode on the left-hand side and write the positive electrode on the right-hand side. So in this way, we place the metals at the sides, and then we write zinc, for example, metal, zinc, solid, and we put a solid line and then, or a vertical solid line, and then zinc ions, aqueous, and then we put double vertical dotted lines, and then we write copper ions, and then a vertical line, and then copper solid. So as you see here, we write the metals at the two ends, and we write the solutions, and in between them, we draw a double vertical line that is dotted. Now, here in the zinc metal / zinc ions, it means that there is a phase boundary between the zinc metal and its solutions. And also in case of copper metal with the copper ions, there is a phase boundary. That's why we put these vertical lines. Now, what are these dotted vertical lines, double dotted lines? It means the salt bridge. When we put double vertical dotted lines, it means it represents the salt bridge between the two half cells. So we write these two half cells in this way, and we can write the E node value of the zinc electrode below it, and the E node value for the copper ion, copper electrode below it. And when we want to calculate the E node cell, which means the standard cell potential, we write E node right minus E node left. It means that we are going to write the standard electrode potential of the right-hand side electrode first, and then minus the second, which is on the left-hand side, which is minus 0.76 volt. So minus makes plus, and this means that the E node cell will be equal to plus 1.1 volt. So if we want to measure the E node cell between two different electrodes, then we connect the one that has the negative value, the negative standard hydrogen, the negative standard electrode potential to the left, and we connect the other one which has the positive value to the right. And when we want to measure the E node cell, we say it is equal to E node right minus E node left, the one that gains the electrons, that has more positive value, minus the one that has the less positive value. This should not always be a negative, it could be less positive. So we say the more positive minus the less positive, and we get their total as the E node cell, the standard cell electrode. Okay, the standard cell electrode potential. Okay. Now there is a special type of writing cell diagrams, is that when we write the standard, how to measure the standard electrode potentials, For example, by adding the zinc electrode half cell to the standard hydrogen electrode half cell, or we connect the copper ion electrode to the standard hydrogen electrode half cell, whether it will give us a negative value or a positive value for the standard electrode potentials. Usually, when we measure the standard electrode potentials, we write the system in this way. It's something that is, always we put the standard hydrogen electrode on the left-hand side and the other one on the right-hand side, even if, for example, the zinc is the one that releases electrons. It doesn't matter. When it is connected to standard hydrogen electrode, the shorthand notation or the cell diagram will be written in this way. Okay. Now we come to find out how we can predict whether a reaction will take place or not, which we call it thermodynamic feasibility. Thermodynamic feasibility means that we want to find out, will a reaction take place or not? So we call this the standard electrode potentials and the thermodynamic feasibility.